So let's start by talking about 3D printing. 3D printing is a lot like normal printing, but it's in 3D. Not that kind of 3D, but more like this. 3D printing refers to additive manufacturing techniques that build objects layer by layer, starting from nothing and ending up with a completed physical object. A common exaggeration is a 3D printer is just like a Star Trek replicator. You can make anything. Although you can make very complex geometries with a wide variety of materials like plastics, powders, and metals, 3D printing does have its limitations. This is why we have so many kinds of 3D printers. These are a lot of different varieties that exist of different kinds of additive manufacturing techniques that fall within the field of 3D printing. The true magic of 3D printing isn't it being a Star Trek replicator, it's how we use it. A 3D printer is used by designers to generate their parts in the real world. So you can take a design, plug it into the printer, and it'll print it out for you. Then you can take that part in your hands, make adjustments to it, change your design, and print out another one. So it's used for iterative design and to actually check parts with the real world. So a really useful tool. A disadvantage of 3D printing is that it's actually pretty slow. So we have a really nice little 3D printed cup over here on the left with an integrated straw, pretty cool. That takes about the same amount of time to print as, or to manufacture as these plastic cups, or 100 packs of 50 plastic cups, so 5,000 plastic cups. It's about the same amount of manufacturing time, and that's lowballing it. So this layer by layer additive process is pretty slow compared to a formative manufacturing technique. So I started getting interested in 3D printing when I was in my senior year at MIT, and I wanted to make a printer that was really fast and really cheap, and printed with a wide variety of materials. And so I was a little disappointed to find out that these goals were kind of what the entire 3D printing industry was already working on. So I decided I needed to take a different approach if I was going to make a big impact in this field. So I kind of looked at the trends that exist within fabrication tools, and you can kind of plot them on this graph here where the flexibility and speed of a fabrication process are inversely proportional. So 3D printing on the left is very flexible, but pretty slow. And injection molding on the right, making Legos, is very fast, but can only make the parts that the mold is designed to make. And I needed something that was both fast and flexible, and sort of our breakthrough technology that jumps out of the curve. I ended up finding out of a little-known field called Reconfigurable pin tooling. You probably haven't heard of it. Essentially, the idea is to have a bed of pins that are adjustable in height, and with those pins, you can generate a surface for use in molding or for other applications. This is from science fiction. This isn't real. I was surprised to find out an interesting fact, though. This is the first patent in reconfigurable pin tooling in 1863. That's 150 years ago. In comparison to 3D printing, the first patent in 3D printing was in 1984. It's 29 years ago. So if reconfigurable pin tooling is so cool and such an old idea, why are there no reconfigurable pin tools while so many different 3D printers exist on the commercial shelves? Well, it turns out they're just really hard to make. So this is a pin art toy. You're probably familiar with this. This is the most classic example of a reconfigurable pin tool. And if I were to make this electronically reconfigurable, I would have to add a motor to every one of these pins, right? And there's about 1,000 pins in this sort of cheap desktop toy. 1,000 motors is a lot of motors. And that's a really significant engineering challenge. You probably, or you might have seen this video. It actually came out these last week. This is a really cool example of a reconfigurable pin display that some of my friends made at the MIT Media Lab. And this device is individually actuated, so all the pins have a single motor on each one. And there's 900 pins with an 3/8 inch resolution, and it was used for haptic interface and for making experimental surfaces. So if I wanted a surface that was higher resolution to use as a mold, why can't I do this? Why can't I make this surface super high resolution? Math, that's why. Math is fighting me on this one. When I increase the resolution, I get this quadratic scaling of the area. So length times width is area, and that's a nonlinear term. So when we get to high resolutions, this becomes a really big problem. We get huge numbers of pins to control, massive numbers of motors, and it just becomes totally infeasible, and everything falls apart. So faced with this hopelessness, I decided to do this for my PhD and master's and undergraduate thesis. And I've been working on it for about 3 years now, and I've developed a number of techniques to actuate pins and to move pins. These are some of the prototypes, and I actually won an award for one of them, which is the reason I'm here, because I got picked up after that. And I was just kind of disappointed in all of them so far, until recently. And that's what I want to talk to you guys about today. So I had an interesting idea when I was working on a different project, not the reconfigurable pin tooling project, but I was working on a machine that had a lot of vibrations in it. And what happened is that I was attaching a part to it, and the screws in that part kept on coming loose. And it was really frustrating at first, but then I realized that I could actually use this pattern vibration to turn out screws, which is actually a really good way of getting linear actuation, so moving something along its axis. So what I decided to do is apply this to reconfigurable pin tooling. And here it is. It actually works pretty good. This is an array of screws that has a specific pattern of vibration applied to it, and that causes selective screws within the array to actually turn out. And you can turn them back in as well. And it works like this. This is a schematic of the actuation here. We have dislocations within this square array of screws. And if you dislocate it just right around the screw you want to turn, and you reset it, you get a nonlinear torque applied to one of these screws, and you get motion. So pretty cool. And the coolest thing about this is that the only actuators you need, the only motors you need for this array is for the edge pieces. So the edges are always going to scale linearly with the resolution versus the number of pins scaling this huge quadratic term. And all the pins have to be are just little screws. Screws are very cheap, and you can get cheap linear actuators on the edges for vibration. And this works really well at high resolutions because that ratio becomes higher and higher as you get higher in resolution, the ratio between linear and quadratic terms within the array. With me so far? All right. So after doing this project, I'm actually pretty confident now, more so than I ever have been in the past, that this HD pin surface could be a reality. And you could see one of these on your desktop and download a file into it and have it reconfigure its surface into an arbitrary file that you find online. And you really use it as a design tool because you could use it as a mold instead of just 3D printing objects layer by layer, or along with a 3D printer as well. So it's really just a close cousin to 3D printing versus any sort of replacement. And here it is. This is kind of the pitch, the digital mold as the next tool to help form and shape the future of personal fabrication. That's it.